and welcome to our course on drone surveying. In today's lecture, we will learn about the concepts behind GIS based integration of drone data such as multispectral imagery, thermal photogrammetry and LiDAR data. So, in order to move forward, let's begin with an example. A municipal corporation is planning to expand road corridors in a growing peri-urban zone, and currently the roadside is partially encroached and they are also facing problem of flooding in some road stretches. And in order to better understand this problem, to include this in their planning, the municipal corporation has already collected cadastral vector maps which contain legal boundaries of land holdings. They have collected orthomosaic imagery which captures present land use including encroachments, and they have also prepared a DEM, a digital elevation model, to characterize terrain, drainage direction and cut and fill cost. However, how to analyze these data for urban planning, for planning of expansion of road corridors. So, we will learn today that through integration in GIS, planners can identify feasible alignments. So, in the previous lectures, we have already studied about some of these drone sensing payloads. For example, visible imaging camera, which provides orthomosaic and DEM using the visible images. Then there is multispectral sensors, which provides spectral band in red, green, blue, red edge and near infrared, which can be used for vegetation health analysis. There is also thermal infrared sensor, which provides surface temperature for crop stress detection, irrigation monitoring, wildfire assessment or building insulation assessment. There are also hyperspectral sensors which provide very high spectral resolution for detailed spectral signatures for different types of material identification. There are also LiDAR sensor which provide point cloud from which DEM, DTM, volume estimation, object detection or bathymetry can be provided. Then there are also environmental sensors which can be mounted on drones, and these are point sensors for in situ measurement of meteorological variables and pollutants. Not only these, there are also more upcoming sensing payloads, for example, drone SARs. So, as can be seen, there are very diverse variety of sensors, and each of these sensors has their own strength and limitation in what they are sensing. So, the strength and limitation can be in terms of spatial resolution, spectral resolution, geometry measurement or in situ sampling. So, essentially no single sensor can capture all dimensions of a phenomena. So, by integrating the data sets from different sensors together, we can achieve better decision making through accurate mapping, feature characterization, detection and so forth. For example, we can consider a case of forest fire mapping and prediction. Through a thermal sensor, we can detect active fire. Through LiDAR sensor, we can measure the damage to the forest biomass, and through environmental sensor, we can measure the impact of fire on air pollution. Further, by using a multispectral sensor, we can map the dry forest which is more prone to burn, and by creating a DTM through either LiDAR or photogrammetry, we can map the slopes on which these fires can spread. And not only that, we may even want to integrate satellite remote sensing data or past survey data from topo sheet, which may even have different coordinate reference system with our drone based data. So, we need some processing to bring various data sets together and relate them to each other. Thus, we need a multi-source data integration for the diverse sensor outputs from drone platforms to generate a comprehensive high-resolution geospatial product that exceeds the capabilities of individual sensors, and this can be achieved through GIS. So, GIS or Geographic Information System is a computer system for capturing, storing, querying, analyzing and visualizing geospatial data at various spatiotemporal scales. So, it is a information technology that helps us understand and relate to the what, when, how and why of the world by answering where. And the main elements of GIS are the geospatial data acquisition, geospatial data management, geospatial data visualization, geospatial data exploration and geospatial data analysis. And these comes with its own set of challenges of interoperability, quality and heterogeneity. So, in GIS, we want to ensure interoperability such that different data sets which may be in different coordinates reference system, we want to bring them in the same coordinate reference system and reference them to the same vertical and horizontal datum. We will see what we mean by this. We also want consistent data quality in terms of spatial or temporal resolution, including errors and gaps. Otherwise, it can lead to inaccurate analysis and decision making. For example, integrating drone data of the year 2025 with satellite image of the year 2020, we have to be very careful in what we are doing. And we also would like to overcome data heterogeneity. So GIS data comes from various sources, each with its own format. It can be a raster, vector, or a point cloud, and each of these sources has their own structure also, which makes it difficult to standardize and integrate. So the main concept in multi-source integration in GIS are coordinate reference system, resampling, and GIS operations. So we will look into these main concepts one by one. So a coordinate reference system, in short a CRS, is a framework for defining and locating features on Earth by assigning a set of coordinates to a point. And the basic principle in GIS is that map layers which are going to be used together must align spatially. They cannot be differently aligned. And data from different sensors are often generated in varying coordinate reference system. For example, drone and satellite and topo sheet and total station based survey, they will all be generated in various coordinate reference system. So integrating these sources accurately requires all data to be referenced to a common CRS, enabling precise overlay and analysis. So the coordinate reference systems which are used in drone survey are primarily two: geographic coordinate system, in short GCS, and projected coordinate system, in short PCS. So GCS is a reference system for locating spatial features on the Earth's surface defined through latitude and longitude, for example WGS 84. And projected coordinate system is a reference system for transforming the GCS on an ellipsoid into locations on a plane. So for example, Universal Transverse Mercator. So to specify actual locations on the physical Earth using latitude and longitude and height, GCS is used. And in the GCS, the main component is a geodetic datum, which is a reference model of the Earth's shape and size. And geodetic datum is of two types. There is a horizontal datum, which is used to measure latitude and longitude on an ellipsoid, and there is a vertical datum, which is used to define the reference surface from which elevations are measured. So latitude, as many of you may be already knowing, are measured northward or southward from the equator to poles, and they range from 0 to 90 degree north and south. So in this, these are all lines of latitude, also known as parallels of latitude. And longitude is measured eastward or westward from the prime meridian at Greenwich, England, to the international date line, and they range from 0 to 180 degree either in east or west direction. So let's say this is the Greenwich meridian or the prime meridian, and from here in this direction, this is in the east direction, we will have lines of longitude. So these are the lines of longitude, and they range from 0 to 180 degree in east or west direction. Now for measuring the heights of points on the Earth's surface with respect to a vertical datum, the height can be with respect to different reference surfaces. So let's see what are these reference surfaces. So first we have a topographic surface, which is the actual surface represented by land formation. Then we have reference geoid. It is an imaginary surface of constant gravitational potential that represents mean sea level globally. So geoid is also known as the shape of the Earth, and there are different models for geoid. For example, European Geoid Model 96. And we also have a reference ellipsoid. Because geoid itself is not a mathematical surface, we approximate the geoid through an ellipsoid. So reference ellipsoid is a mathematical model that approximates the shape and size of the Earth. For example, WGS 84 ellipsoid or the Indian ellipsoid Everest. Then in this image, we can see first of all the topographic surface. We can see undulations on the Earth. Then we can also see the mean sea level, and the mean sea level represents the geoid. So as you can see, geoid cannot be approximated by a mathematical shape. We have mathematical approximation of geoid known as the ellipsoid. So ellipsoid is an ellipse rotated about its semi-minor axis. This is the ellipsoid. Now depending on which surface is being used for measurement or for referencing the height, we have different terminologies. There is ellipsoid height, which is the height measured from the ellipsoid, and there is also orthometric height, which is the height measured from the geoid. For example, GNSS provides us ellipsoid height, but because ellipsoid height are not really useful in most of the engineering works, in civil engineering works for example, therefore we always would like to convert from the ellipsoid height to orthometric height. So this was about specifying coordinates on the 3D representation of the Earth. Then we also have projection of the 3D surface of the Earth onto a 2D flat plane. So a map projection transforms the geographic coordinates on an ellipsoid into locations on a planar surface. For example, universal transverse Mercator. So the projected coordinate systems are also referred to as rectangular coordinate systems or planar systems or grid systems. And in these projected coordinate systems, the x value is specified first and is called easting, followed by the y value, which is known as northing. The image below shows the projection of geographic coordinate system on the left side into a projected coordinate system, which as you can see is on a 2D flat surface. And essentially this leads to conversion from latitude and longitude to easting and northing. Now the map projection can be performed with the help of projection surfaces. So projection surfaces are planar, conical and cylindrical. So you can imagine you are wrapping either a plane or either conical sheet of paper or cylindrical sheet of paper onto the globe, and you are projecting the globe onto this paper. And once you open the paper, then the representation of the globe that you will get on that sheet of paper will be the map projection. So we can see examples of how planar, conical and cylindrical projection of the globe and how the grids appear on these projections. Then map projections are grouped by the property that they preserve. For example, there are conformal map projection which preserve the angle and shapes of the feature on the globe. There is equivalent map projection which preserves the relative area of the feature on the globe. Then there is equidistant map projection that preserves the scale along lines, and there is also azimuthal map projection which preserves the direction of different features on the globe. Then usually the most common or popularly used map projection is the Universal Transverse Mercator, in short UTM. It is a secant transverse cylindrical projection, which means instead of having a upright cylindrical, we have a cylindrical in a transverse position. So this is a cylindrical in a transverse position, and because the cylinder intersects the globe at two places, so we can see it intersects over here and here, that's why it is known as a secant projection. So this secant transverse cylindrical projection divides the surface of the Earth into 6-degree zones. So this is one of the zones and this is 6 degree, and there are 60 such zones. So overall we have 360, we cover the 360 degree around the globe with a central meridian. So this is central meridian in the center of each zone, and each zone is a different transverse Mercator projection rotated slightly to use a different meridian. Then UTM zone numbers designate 6-degree longitudinal strips extending from 80 degrees south latitude. So this is 80 degrees south latitude to 84 degree north latitude, and UTM is a conformal projection. So small features appear with a correct shape and the scale is the same in all directions, and UTM coordinates are in meters, which makes it easy to make accurate calculation of short distances between points on the surface of the Earth. So this shows the UTM or Universal Transverse Mercator system, and we can see there are 60 such zones starting from 1 and 60 is over here, and India falls under UTM zone 42 north and 46 north. So 42 north and 46 north, most of the Indian region falls in this zone. So we have seen what are the coordinate reference system. Now sensor data sets, for example drone based LiDAR, drone based camera or satellite remote sensing based data are often in different coordinate reference system. To bring them into the same coordinate reference system for accurate overlay and analysis, transformation and reprojection is necessary. So, transformation, also known as geographic or datum transformation, is a mathematical process to convert spatial data between two different geographic coordinate systems, which are based on different datums or model of the Earth shape and size. For example, converting from the North American datum of 1983, NED 83, to the World Geodetic System of 1984, WGS 84. And we also have reprojection, which is a mathematical process of converting data from one projected coordinate system to another projected coordinate system. And these transformation and reprojection, they are performed using GIS software. For example, QGIS, ArcGIS or GDAL tools. And as a user, we always specify target coordinate reference system based on the project requirement. For example, if I'm conducting my drone survey in a specific region in India, then I will first figure out what is the UTM zone for that particular region, and based on that, I will specify the CRS. So, through reprojection and transformation, the coordinate reference systems of the datasets from various systems have been harmonized now. However, the dataset may still have different grid orientation or grid size in terms of spatial resolution per pixel. Therefore, a uniform grid alignment and resolution is needed, which can be achieved through co-registration and resampling. And only after co-registration and resampling, the integration of different drone sensor based data can take place. So, adjusting pixel size and assigning new values to the pixel during realignment of the grid while we are matching one data set to another is co-registration and resampling. And this ensures all raster datasets share the same spatial resolution and grid alignment for direct comparison and computation. And this is especially needed when fusing data from sensors with different native resolution and when datasets have undergone reprojection. For example, in the left image, we can see an example of co-registration, in which there are two image datasets, but their grids are not aligned with respect to each other, and which can be achieved through co-registration. On the right side, we can see an example of resampling, in which there are two datasets, but as you can see, the pixel resolution of both the dataset is different. So, on the right side, we have resampling. Both co-registration and resampling can be achieved through operations like nearest neighbor, bilinear interpolation, and cubic convolution. And these are some of the most popular methods. There are even more advanced methods. So, nearest neighbor is a resampling method which assigns a value to each corrected pixel from the nearest uncorrected pixel. The advantage of nearest neighbor includes simplicity and the ability to preserve original values in the unaltered scene. The disadvantages include noticeable position errors, especially along linear features where the realignment of pixels is obvious. So, nearest neighbor is therefore preferred whenever we have discrete data and not when we have continuous data. For example, if we have land cover classification at certain resolution and we want to upsample it, in that case we prefer nearest neighbor because we cannot have an interpolation of land and water class. Either a pixel will be land class or a water class. In such situation, nearest neighbor is preferred. But whenever we have continuous data like elevation or temperature or rainfall, then bilinear interpolation or cubic convolution interpolation are used. So, bilinear interpolation works by interpolating between the 4 pixels nearest to the point that best represents the pixel. So, usually it is in the middle of the pixel. And cubic convolution determines the pixel value through a weighted average of 16 closest pixel to the input coordinates. It is generally better than bilinear interpolation and it does not have the disjointed appearance of nearest neighbor interpolation. But cubic convolution requires about 10 times the computation time required by the nearest neighbor method. So, there is a trade-off between the computation time and resources which is required, but there is also an advantage in cubic convolution that we get more smoother looking result. Then despite the different interpolations, there are still sources of uncertainty. First major source is because of spatial mismatching. So sensors will have the differences in terms of resolution. For example, RGB camera may have a 2 centimeter ground sampling distance, multispectral camera may have 8 centimeter ground sampling distance, while thermal may have 12 centimeter ground sampling distance, and a LiDAR point density may be 50 to 200 points per meter square. And because of these differences in the density or the differences in the sampling distance, it creates a scale dependent integration challenge. So whatever phenomena is visible at 2 centimeter ground sampling distance may not be visible at 12 centimeter ground sampling distance. So that creates scale dependent integration challenges. Then there is also variations in the field of view. Thermal sensors have narrower field of view than RGB cameras. So this affects their coverage and overlap geometry. Further, there may be difference in the focal length of the camera which has been used, which will again lead to differences in coverage and overlap geometry. So some of the solutions are either we can address them at the data acquisition stage itself by careful flight planning, which will ensure sufficient overlap by 70 to 80% in forward side and 60% in the side lap. Or sometimes we have methods which we can apply in the post-processing stage. For example, multi-resolution segmentation algorithm can help account for these scale differences. Further, there is also uncertainty on account of temporal mismatching. So there is multi-flight variability which can lead to differences in illumination, phenological stage and weather condition between flight, which will affect the radiometric consistency. So let's say if part of the scene is acquired during noon and part of the scene is acquired during evening, then there will be different illumination condition. Then there is also sensor drift during flight. So thermal sensor, they experience temperature drift in the first 10-15 minutes after takeoff, which can also cause systematic error up to 4 degrees Celsius if they are uncorrected. So solution is to fly during stable illumination condition, so 2 hours plus and minus the solar noon for multispectral cameras. Or another solution can be to have repeated ground reference measurements during flight, so every 1 to 2 minutes for thermal calibration. And another solution can be radiometric normalization across multi-temporal dataset. So these are not perfect solution, but to certain extent they help us overcome the uncertainty which is caused because of temporal mismatching. Now after a uniform grid alignment and resolution is achieved, then data sets from different sensors can be analyzed together. Their integration can take place at multiple levels. It can be either pixel level, feature level or thematic level, and this is achieved through GIS operations. So GIS operations provide method to combine, compute, compare, re-express and summarize multiple spatial layers, and they enable quantitative and spatial relationships to emerge. So derived layers from GIS operation, they contain enhanced thematic information which can be used for decision making. For example, suitability, hazard ranking, exposure metrics and so on. So GIS operations are primarily classified into 3 categories. It can be a raster operation, it can be a raster vector operation, and it can be a vector operation. So in raster operations, we have map algebra, weighted overlays, logical overlays. In raster vector operation, we have zonal statistics, sampling, and conversion from raster to vector or vector to raster. And in vector operations, we have topological overlay in terms of intersection and union, proximity operations through buffering, and spatial joins. So mostly drone data is in raster form, hence raster operations and raster vector operations are most commonly performed. So the raster operations are cell-based computations on gridded data, and for this the input layers must share spatial reference and alignment. And raster operations are also sub-classified into 4 categories: local, wherein the operation on the pixel only concerns that particular pixel, or it can be focal, where operation on a pixel also takes into account the neighborhood of that pixel. It can be a zonal, where operation on a pixel takes into account all pixels falling under a certain zone, and it can be a global, where operation on a pixel takes into account all the pixel in the given scene. So, local operations are also known as point operations, while focal operations are also known as neighborhood operations. And local operations, they operate cell by cell. And examples of local operations are overlay operations, scalar operation, reclassification operations. An example of focal operations are slope and aspect calculation, image filtering, or image enhancement. So, I would like to now show some example of raster operation applied on a local level. So, this is an overlay operation. So, raster overlay combines multiple raster layer to create new data set. So, on the left side we have three different rasters A, B and C, and there is some weighting scheme that has been applied. So, raster A will be weighted by 25%, raster B will be weighted by 65%, and raster C will be weighted by 10%. So, which means each pixel of the raster A will be multiplied by 0.25, each pixel of raster B will be multiplied by 0.65, and each pixel of raster C will be multiplied by 0.1, and then they will be added up. This will be the result of the overlay operation, which is applied on a pixel by pixel basis. So, for example, we have 8 over here, which is multiplied by the weight of 0.25, then we get 2. 7 multiplied by the weight of 0.65, we get 4.6, and 4 multiplied by a weight of 0.1, we get 0.4. Then sum of 2, 4.6 and 0.4 is 7. Right? So, this is an overlay operation. Then we also have raster vector operation, an example of which is zonal statistic. So, zonal statistics operation is one that calculates statistics of raster cell lying within the zones defined by another data set. Zonal statistics operation is fundamentally a raster analysis performed on two rasters, in which one is the zone and other one is the value. However, if the zone is defined by the vector, as the case for raster vector operation, then first the vector is rasterized and then an overlay operation takes place. So, for example, in this image, we can see the input value raster shown in the gray and blue pixel. On top of that, there is a zone which is specified by a vector. So, first of all, the zone, or first of all the vector is rasterized. So, this leads to a zone rasterization grid. So, we have a zone rasterization grid. Then from that, the rasterization zone is identified. So, we have then identified the rasterization zone. So, these are the rasterization zone, and then the rasterization zone is overlaid on top of the input value raster, and through this the zonal statistics operation is achieved. Now, we will look into the applications of multi-source integration in GIS. So, there are various types of applications. I am just giving a very small subset of those applications. For example, to analyze heat stress in urban areas, multi-source integration can be achieved by combining land surface temperature from thermal sensor with land cover from multispectral sensor and building height from normalized digital surface model. Then such integration is used in precision agriculture for combining plant health from hyperspectral camera and its impact on crop yield, which can be measured through a LiDAR camera. Then it is also used in disaster, for example in floods, where by combining the surface water from multispectral camera with the normalized digital surface model, which can be used to represent the building height, and these together can be used for estimating the flood impact on human. The applications are also prevalent in the energy sector. For example, in solar energy, by combining the normalized digital surface model with land cover from multispectral images, it is possible to identify feasible location for installation of solar panels. And also in environmental applications such as in wetlands, by combining the water quality measured through hyperspectral camera with gas emissions measured through thermal and laser sensor, we can identify which wetlands are contributing to different types of gas emission. So in summary, we saw that data integration in GIS combines heterogeneous geospatial datasets to support analysis, modeling and decision making. And this requires pre-processing. So we need to standardize coordinate systems, we need to standardize projection, resolution and radiometric properties. And by doing so, it enables GIS analysis through overlay and fusion of multiple layers, which can provide tool for monitoring and decision making. So that was all for today's lecture. Thank you very much.